Welcome to The Explainer. Today, we are tackling a really fascinating question, one that's right at the heart of all this modern tech we're seeing. So you've probably wondered, right? How can a machine just write a poem, or spit out code, or even draft an email for you? It really does feel like magic. But, and this is the key thing, the secret isn't just about throwing more and more computing power at the problem. The real answer, well, it's not in some brand new complex code. It's actually hidden in this simple, really elegant principle of efficiency. And to get it, we've got to look away from Silicon Valley for a minute. We're actually going to journey back in time into a pretty dense academic text about, well, about human language itself.
Right, so here we are, an old linguistic secret. We're diving into a work called Existenzformen der Sprache, which, translates to the forms of existence of language. This actually came out of the Soviet School of Linguistics. Pretty fascinating stuff.
Okay, listen to this quote. Where should one find the tens or hundreds of thousands of different names for all the birches, faces, and chairs one has seen? Think about that for a second. Our brains can't possibly have a separate, unique memory file for every single thing we see, every chair, every face. It's just too much. It would be completely overwhelming. So how does our brain handle this information explosion? Well, it follows this really fundamental rule, a rule that linguists back then called the Gesetz der Ökonomie, or, as we'll call it, the principle of economy. And this is the whole idea right here, the principle of economy, or Sparsamkeit. It's this natural tendency for any complex system that's dealing with information to get efficient. It creates this infinite, complex world of meaning from just a small, finite, and super efficient set of building blocks. Language didn't evolve to be complicated. It evolved to be incredibly efficient, to do the most with the least. And here's how it works in practice. It's a beautiful, elegant system. You start with just a small set of sounds. We call them phonemes. Then you combine those sounds into a bigger, but still limited, set of words. And then, this is the magic part, you use grammar to arrange those words into a basically infinite number of sentences. So you see, from a handful of simple sounds, we can generate millions and millions of ideas. And this system is super flexible. It's not about one right way to do things. Take German, for example. They have one word, Uhr, for a clock on the wall and a watch on your wrist. But in English, we split that. We say clock for the wall and watch for the wrist. Neither system is better. They're just different, equally economical ways of grouping the world into concepts. The building blocks might change, but that underlying principle of economy, it's exactly the same. Okay, so let's fast forward from old linguistic texts to today, because it turns out that exact same principle of economy, that is the absolute key to understanding the mystery of modern AI. And here it is. This is the big aha moment. When large language models were faced with the exact same problem, a flood of information, they independently came up with the exact same solution. It's this beautiful parallel. Where we have sounds and letters, they have tokens. Where we have words and concepts, they have something called embeddings. And where we have grammar and syntax, they have their model architecture. It's the same blueprint, just with different materials. So let's talk about those tokens. What are they? It's just the AI's version of letters or sounds. It's a process called tokenization, where you break down all this text into small, manageable chunks. These can be whole words, or parts of words, or even single characters. They become the fundamental building blocks that the AI uses to construct, anything, from a simple email all the way to a Shakespearean sonnet. Okay, but wait a second. You might be thinking, economical? These AI models are huge. We're talking about some having 1.8 trillion parameters. Compare that to the human brain's 100 trillion synapses. That doesn't exactly sound small or efficient, does it? It seems like a contradiction. And here is the absolutely brilliant twist. Yes, the model is enormous, but it's lazy by design. It uses something called a mixture of experts architecture. So for any single thing you ask it to do, it only wakes up a tiny fraction of its total brain power. For example, some models might have 8 different experts inside, but for your specific question,
It only calls on two of them to do the work. It's the ultimate act of being efficient with your resources. It's computational economy at its finest.
So where does this leave us? What does this all mean? This incredible parallel between how our brains work and how AI works, it's not just some clever engineering trick, and it's definitely not a coincidence. There's this idea that, and I quote, "This convergence suggests universal principles of information processing." Basically, it suggests we've accidentally stumbled upon a fundamental law of the universe for how any complex system, whether it's biological like our brain or artificial like an AI, learns to efficiently manage complexity and information. And that leaves us with a really big, kind of provocative final thought. If both nature and machines arrive at the exact same solution to solve the same problem, then what is intelligence really? Maybe, just maybe, it's not about the hardware it's running on, whether that's a brain or a silicon chip. Maybe intelligence is just about these elegant, economical principles, this universal software that can run on anything.